Hey, all right. So I am doing a redo acid-base titrations. I'm going to do this again, wing it. It's going to be good. I hope so. All right. I'm sorry that I sniffle, y'all. I bend over, leaning over. Let me just tell you, I have like 10 more videos. Excuse me. Gray screen. Favorite color. Okay. What are we going to talk about? We're going to talk about acid-base titrations, okay? And first we're going to look at strong acid, strong base titrations, right? And we already know that that's a net ionic equation, simple as that. And it's really simple to handle. If you look at a titration curve, it will be a volume titrant added. That is what is in the burette, okay? This is your titrant. We're going to say that it is sodium hydroxide, all right? And down here, you have your flask. Oh, goodness gracious. And that will be, you know, I'm going to have to fix that. And that will be your strong acid. Oh, my goodness. And that will be HCl, okay? As you know, we need to put an indicator. The indicator is one color in an acid and a different color in a base. All right, so when we see that indicator begin to change colors, we know that we have reached our equivalence point. Okay, now the end point is when you stop the titration. When you stop adding titrant to analyte, that is the end point. You've ended your titration. Okay, what you need to do is you need your end point to occur at the equivalence point, right? That's what you want, right? This is what you need. You need to ensure this, right? And you do that by looking at the color change of the indicator, because it's going to ever so slightly change right when that H and OH, right? Because if we have a drop excess of this, we're going to see a change start to happen. And you see it where it takes a long time to get that color. You have to experience it. It's fun. Okay. So the equivalence point is the point when H equals OH, right? So you obviously, the point when I'm just going to write H equals OH. So you need to end your titration when they're equal, okay? And an indicator allows us to do that. Now, you choose an indicator. Indicators best indicator has a pH equal to the pKa. All right. That's how you're going to choose your best indicator. So if you have a pH of equivalence point, right? We'll talk more about that, needs to be equal to the negative log of the Ka of the indicator. Okay. I think I did that right. I think, to be honest with you, I'm pretty sure I got that right. So let's go back to our curve. Over here will be the pH. Curves will start, you know, obviously, if we are initially an acid here, we're going to start low. How low depends on the pH, right? It could start here. It could start here. It could start here. So be mindful of that if you are to draw a curve be mindful of where you start your curve of could be held. I have made the mistake of not doing that. So be mindful of your initial pH, okay? And that is the pH before you've added anything. And that pH would strictly be based off of, right, the negative log of the concentration of the HCl, because that would be equal to the negative log of the concentration of the H, right? So the initial pH would be very simple to get. We already talked about that. Yeah, we did when we talked about acid-base reactions. Okay, so as I have my H here at a particular pH, whatever it might be, and I begin to add my titrant, my OH, we see that the pH begins to go up because we are losing our hydrogen ions. So we have a decrease in hydrogen ions. We have an increase in our pH. And then we'll see a spike, and then we'll see it go like this. And when we have the strong acid, strong base titration, our equivalence point here, the center of this spike, mine doesn't look so perfect. It should, guys, be the center, right? It should be the center here. What we would have is the equivalence point. And if it is a strong acid, strong base, that will occur at 7, okay? Because we have those weak conjugate acids and bases is the only thing present in the solution. Weak conjugate acid and base, only thing present. Okay, so that's it. That's it. You can look at this and see that the equivalence point is at 7. So we know it's a strong acid, strong base. I could also, based on this curve, I could see the volume of titrant needed to react with all acid. Therefore, can determine the moles of acid in the titrant, analyte, sorry. Right, and I can from there get the concentration of that. You've done those things, right? Okay, let's talk about, and also, right, we would need an indicator that had a pKa around 7 if strong, right? Right? And that would be phenolphthalein. That is the best indicator to use in that situation, okay? And it's going to be pink in the base and clear in the acid. Okay, I've got to get to class. Now, next, let's look at a weak acid. Not a strong acid, but a weak acid, strong base, okay? Now, I don't want this to take too long or to be too difficult. Boom, boom, volume, base, right? That's going to be hydroxide, and this will be the pH, 14, 7, whatever, okay? Now, yes, we'll start below. The pH initially is just determined by, you know, your equilibrium expression. We've already talked about that, right? This is going to be X over the concentration. Sulfur X equals H, right? So we use the Ka equals X squared over the concentration. And then the pH equals the negative log of H. So that will be our initial pH, okay? And then that's how we would get that. And we proceed, I think we've already talked about that. We get to our let me think real quick of where this needs to be. Okay, I need to try to change that curve a little bit because what we're going to see happen is something more like that, okay? Here in the middle of this region is our halfway point. We've talked about that. Remember, at the halfway point, the pH is equal to the pKa because the weak acid is equal to its conjugate base. This is your EQ point, all right, and it is in above 7. So at the pH, at the equivalence point, we actually have a basic solution. That is because due to the presence of conjugate base A of weak acid. All right, and A will be in the water and find equilibrium to make HA and OH negative. And that right there is why you're basic. So if you see a curve that has an equivalence point that is above 7, then you know that you have a weak acid and a strong base, okay? Lastly, if we have a strong, oops, that's a horrible color. If we have a, we would need a strong acid. This would actually be a weak base rather with a strong acid, all right? I'd also like to go back up here and say that this region right here is your buffer zone, right? That's when the solution can resist a change in pH upon addition of an acid or a base. This here is your ideal buffer because you have more room to go in either direction. All right, if you add the acid, right, it'll send you here. If you add the base, it'll send you here. But in that length there could almost reference your capacity. Talk about that later, actually. Okay, so we were here. We'll have this. Now, guys, I'm so bad at this curve. I literally can't do it. And this would be H plus added. This would be your pH. We would start high, right? And then kind of go like that. I'm not very good at that curve, but the equivalence point here will be below 7. Therefore, acidic at the equivalence point, right? And we just need to talk about why. First of all, this would be your halfway point. So we would say that the we would say that the POH is equal to the PKB. And we know that the base is equal to its conjugate acid. And at this point, we would have more base. And at this point, we would have more conjugate acid. At this point, we would have no base, only conjugate acid. The presence there, this will establish equilibrium. As such, oops, let me fix that. Producing hydrogen ions, and the pH will be less than 7. In fact, the pH, right, we would do the Ka equals the x squared over the concentration, right? We would just do all of that or whatever. Let's just go like this. It would equal H plus B negative over HB, and then the pH would be equal to the negative log of the H. All right, guys, listen. That's the hardest stuff we have, right? We're good. You got that? You're good to go, okay? You got this. Love some equilibrium.